can't eat grass.
Okay, we are alive, definitely, you can tell. All right, so I'm starting with one of my old demonstrations, okay? And this is the nitric acid and copper demo. They say that this is the first demonstration ever, okay? So this is a nice demonstration. I put copper in here. We all know, based on the net potential table, that if I add hydrochloric acid, the proton isn't strong enough to yank away the electrons from the copper. But the nitric acid is, and again, you just never know when you're going to need it. So if you're not sure why copper, okay, can react with nitric acid, well, here it is, okay? Okay? There's the H+. H pluses are not a strong enough oxidizing agent to yank the copper. It would make negative volts. But if I want copper to oxidize, I need a stronger oxidizing agent. And believe it or not, NO3 minus is. Okay, NO3 minus is.
1, 2, 3.
Okay? Okay, so NO3 minus is, and why is it? Well, because it's an N surrounded by 3 O's. We'll learn its structure at some point. But the whole thing is -1. Hey, -2 individually for these guys. Well, we'll do it like that. Okay? So -6 overall. If I write NO3, the whole thing is -1. It's a cluster polyatomic ion. So it's -1. There's -2 individually for the oxygen. -6 overall. What charge must the N be for the whole cluster to be -1? +5. So party people, we've got a +5 in the middle with very electronegative atoms. Of course, this is an electron sink. We don't think of the nitrate ion as being anything other than a spectator, but that is incorrect. It is an oxidizing agent and a strong one at that. Okay? So it's not just, it does spectate in a lot of areas, but it also can act upon things if there's a high enough concentration. So in this nitric acid demo, let me just play it because it ties into our next crystal field splitting. Okay, so any case, all right, let's play this baby. And I'm going to cut. Okay, so what we have here is, yeah, okay. So I'm putting in my copper, okay, a beautiful little copper into this flask. All right, and I'm going to jab a joy here. So now it's in a round bottom flask.
That's crazy.
Oh yeah, it's crazy how I did that. I'm going to add hydrochloric acid. Okay, this is concentrated hydrochloric acid. Okay, I still have my wedding ring on. I don't wear it anymore because it cuts my, my hands swell when I get nervous, and it cuts like my fingers get blue. All right, so I added hydrochloric acid here. Nothing's happening. The proton, I'll bring it up. The proton's not strong enough to yank electrons. It's not a strong enough oxidizing agent. So what I do now is I'm going to put some nitric acid instead. We know it's not the H plus from nitric acid. Nitric acid, of course, is HNO3. Yes, it dissociates into H plus, but it's the nitrate ion with that N+5 in the middle that absorbs. So by pouring the nitric acid, okay, now we've got a reaction. Now that brown reddish gas, okay, is NO2. Okay, so the nitric acid or the nitrate ion, okay, that's acting upon the copper is going to NO2. Okay, we know that this is +5. What's the charge? What's the oxidation state of N here? +2. Well, and the +4 actually, because this is -2 individually. There's 2 of them. -4 overall. The whole thing to be 0 is +4. There's only one N, so it's +4. So you can see that the charge of the N is decreasing because the nitrate ion is doing what? The nitrate ion is grabbing an electron from the copper. Now what's cool is I put this top on and I'm pushing this brownish red gas through the water. There's a reason for that. Okay? The reason why there's a color here, okay, is something we're talking about too. The color is associated with transitional metals. In any case, so this brownish red gas is here, and we're pushing this forward. Now, as the reaction reaches completion, I don't know why, either I run out of copper or I don't have a nitric acid. In this case, I think I added enough nitric acid, so I think the copper limits the reaction. So at some point in this reaction stops. Heat was given off in this reaction, okay? So now as this cools, the gases that were given off are slowing down. The pressure hitting the top of this liquid layer is going to force the water up. As this cools, we make a partial vacuum. The pressure on the outside, we notice we're pushing water back up this tube. Why? Because the gases are cooling here. The reaction stopped. There was gases at a higher temperature flying around. As the temperature dropped, the gases who created pressure slow down. And what's happening is pressure on the atmosphere is higher. And now I'm pouring water back like a siphon. You notice the water's going down and I'm filling this. Now look at the color here. That's the key here. And that's the cool part of the reaction. What's the color right there? Yeah, and that's the color of copper ions.
That's so cool.
That's really cool. And we looked at, so there's your copper ions, and there's no copper left. All the copper became copper plus 2. But the question is, why does copper give us that blue-green color? Why? There's something that transitional elements do. Transitional elements, party people, are those elements that are transitioning from the most reactive big metals into the smalls, the non-metals. Okay? In Regents chemistry, you just memorize that transitional elements, if I can ever find the periodic table, okay, gotta have that one ready. You guys learn that transitional elements in Regents chemistry, okay, have colored solutions. That's not good enough here, okay? So our transitional elements are right here, okay? They're transitioning from the bigger atoms to the small ones. And there's something special about them. They have an ability to lose many electrons, okay? And they're pretty small on top of that. We talked about manganese. If you look carefully at manganese, it can be +7. In this Regents chemistry table, we can see that manganese can become +7. I don't know if it's clear enough, and if it's not, I feel bad, but now I'm over it, okay? So manganese can be +7. We know that's purple. But manganese +2 is clear. Okay, that was a lab we just did. Copper +2 has a color. Believe it or not, iron +3 has a color. But iron +2 doesn't. There's something about these metals with high charges and being very small that creates something called complexes. What's a complex? Well, we talked about this in acid and base. Okay? What's a complex? Well, in the case of copper, here's the complex. Copper is, if it's +2 and pretty small, okay, what does it do? It pulls in the water molecules. In fact, it pulls in 6. I'm going to try to draw 6, but it makes this complex. And it pulls in the negative part of the oxygen. Why? Because it's gosh darn so what? Attractive. Its force of attraction is high. Coulomb's law. The force of electrostatic attraction times a constant times the size of the charge of the positive, size of the charge of the negative, over the distance squared, or r squared. These guys have high charges and they're small. They have small diameters or radii, and they have pretty high charges. In the case of copper, it's not so big, but big enough. They create an incredibly high force of attraction. So much so that the outermost electrons of the oxygen actually invade the electron space of the copper +2. And we write these guys because they are, some people think they're covalently bonded. We write this complex as copper, 6 waters, because only 6 can fit. And we write +2 because the ion is still +2, and this is called a complex. Transitional metals make complex ions. They're not just copper +2 floating around and water's attracting them and breaking off. There's definitely 6 that are pulled in so tight. And those definite 6 are making some sort of bond, or they're interfering with electron clouds. Some people will talk about exactly what that is. And because of this, okay, they create a color. Sort of. It's part of that. That's called crystal field splitting. Okay? And I'm going to talk about that today. And it's the color that they create by having those electrons interfere with some of their electrons, okay, that's what we're going to use in something called spectrophotometry. Spectrophotometry is a device that measures how much light they are absorbing. If something has a color by the negative theory of light, it's because that the electrons are absorbing part of the visible spectrum, and the part of the spectrum that they're not absorbing gets transmitted back to you. The easiest definition is whatever it doesn't use reflects back. In truth, it's retransmitted. Atoms have electrons in different energy levels. And if these guys can absorb these energy levels, so electrons can jump to higher energy levels farther away, then they're going to take part of the visible spectrum. And therefore, what they don't absorb, they transmit back. Classic case is chlorophyll. We know that what? Chlorophyll makes things that photosynthesize, usually green. Most plants are green. Why? Because chlorophyll, the photosystems, okay, in the thylakoids of the what? Chloroplast, remember that? Okay, give off a green color because they absorb both the red and blue part of the spectrum. They don't use the green. The green is retransmitted back. So we're talking about spectrophotometry as a way to measure the concentrations of things that have color. That's what we're doing in the next lab. But I need to talk about why transitional elements, okay, that make these complexes have a certain color. Okay, so let's get there. All right, so talking about that. All right, well, again, here's an example of a graph from a spectrophotometry experiment that we did a couple of years ago, okay? And we do this in AP Bio, and we take the spinach leaves, and we take the pigments from the spinach leaves, and we dissolve them, and we run them through a spectrophotometer, okay? And we can see from this lab that the chlorophyll absorbs the blue end of the spectrum. Remember, it's Roy, red, orange, yellow, green, right? Okay, this is the Roy G. Biv. So the lower energy light, the higher energy light, but because they absorb both ends of the spectrum, what they are not absorbing gets transmitted back, and that's why chlorophyll is green. It's the negative theory of light. The positive theory is if you take a dark room and you shine like stage lights, you can mix lighting as well. Our eyes work by the positive theory of light. We have black orbs that absorb light, and we add photons to get the light. This is light is hitting it, and then of course what's not using. That's kind of like paint. Paint is the negative theory of light, okay? Because you need light, okay, to hit it to show what's not being used in the pigments of the paint, okay? Someone's wearing a blue shirt, okay? I think that's blue, or is that green? I don't know. It's blue, okay? Well, we're seeing blue because the yellow part of the spectrum is being used by the pigments in your shirt. That's the negative theory of light. That's how it works. If you have black, okay, why is it black? Because the chemicals in the black here are taking in what? All of the spectrum. That's why if you wear black in the summertime, you're going to feel warmer. You're absorbing all the wavelengths of light, and it's going to get warmer. If you're wearing white, there's a reflection. You feel cooler. You're not absorbing that energy. Okay, so that's just some basics. We'll do more of that. Yes?
What about brown?
Brown is a mixture, okay, of definitely, brown is a hard one. Obviously it's not one of these here, but I think it's a mixture of things. I'm thinking it's a black with a red maybe, I'm not sure, and something else, the brown is an interesting one. You don't ever see brown fireworks, nor do I think you want to. Oh, that was a brown one!
We forgot to add water into the juicer.
So, here is what they have. Transitional metals have properties that leave them absorbing visible light. They're smaller because usually they can lose what? A lot of electrons. Now, copper plus 2, because it's over here with a lot of protons, starts out pretty small. Losing 2 makes it small enough to do this. But manganese, or manganese that we used in potassium permanganate, what was its charge? What was potassium Mn O4? What was its charge?
Or the whole thing?
With the whole thing?
+7. So when you had Mn O4, you can bet that +7 is going to attract a lot of the what? Water molecules tightly. That +7 pulls them in, okay? Now they also have multiple oxidation states, but more importantly, they have d orbitals. That's what I'm going to talk about today. We haven't talked about electrons in what orbitals. We haven't gotten into quantum mechanics, but I'm introducing this because we're going to use this quantitatively. I'll talk about it another time. But in any case, when you see a complex written, okay, the ion keeps its charge. We're just adding the 6 waters, and they're pulled in because of Coulomb's law. And the reason that they're able to take part of the visible spectrum is what is happening here as these electrons jump into the cloud of electrons because they're pulled in so gosh darn tightly. Okay? Now, here's another demo I think I played last week. I can't do this one live. I'm not doing any live. But this is a what? +6 orange compound that becomes +3. So this is also crystal field splitting. It has a color, even though it's not in water, it can actually doesn't have to use water to do that. Okay? Things that attach to an ion like this, we call these ligands. Okay? This is a ligand. And there's many different types. Water is an example. Okay? So we can have other types of ligands. All right. So let's just jump into crystal field theory because it's really important to understand where these colors come from, and then I'll go back to show some other things that happen here. Okay, so let's make this up close and personal. Now, crystal field splitting, okay, or crystal field theory explains why gemstones have colors, why a ruby and sapphire have colors, okay? And rubies and sapphires, if they're cut a certain way and obviously their purity and their color and their brilliance is all different types of properties people measure to say how expensive or how rare they are, okay? Their color basically comes from a cheap compound called conundrum. And that basically is aluminum oxide. Everybody has aluminum oxide in their crust. Aluminum oxide is what we make aluminum from. We heat it, break off the aluminum +3, we put in a cathode, it's negatively charged, electrolytic cell, we make aluminum. But if there are just a few enough of these other atoms around, they can create this pulling of electrons to make color, okay? So all of the gemstones, ruby, topaz, sapphire, emerald, aquamarine, what they have is they have this corundum, I always say it wrong, the corundum mineral, which is aluminum oxide. It is almost worthless, okay? But if you have a few chromiums instead of aluminum, that'd be a substitutional type of scenario, not an alloy, but in the crystal, if you have just a few enough of these chromiums, it becomes a ruby. And if you have this compound and you have manganese, just a little bit of it for the aluminum, you get amethyst, okay? Topaz. So essentially, just adding a few of those compounds creates this crystal field theory, or this crystal field splitting, so to speak. Now, why does it do that? Well, it's because of its electron arrangement that interferes with the other elements in that crystal. So here's an example, okay? So here's aluminum +3, okay? And here is your hydroxide ions. If 1% of aluminum +3 is replaced by chromium +3, you get a red color. Okay, why red? Because you're transmitting back out the red, which means probably the blue part of the spectrum and green is being used. And why would it be used? Well, the chromium +3 being smaller and is going to do what? Attract electrons from the oxygen into it. Okay, just like the water would be. And create a scenario where electrons are in a certain arrangement that it can absorb wavelengths of light, okay? So it's not just solutions, okay? It happens, of course, due to, here's aluminum, not a transitional, and it deals with chromium, who is a transitional. These guys have something that this one doesn't have, and that is called d orbitals, okay? And I'll explain very shortly. Okay, so now, we learned about this in the summertime. We're going to go back to these configurations. So this is the configuration of aluminum. It has 2, 4, okay. Aluminum +3 has 10 electrons, okay. Now, chromium, being a transitional element, has these d electrons. Now, I'm not going to get into great detail here, but the d orbitals, these are where pairs of electrons can exist, have these crazy shapes. There's 5 different pairs of them, okay? So if you're a transitional element, you're in that middle area that I just talked about, okay? You have these electrons where d orbitals exist. That's really the key here for making colors. In Regents chemistry, we say you need to be a transitional element to have color, okay? And the real reason is because you have these funky shapes where 2 electrons can exist, all right? You're going to learn that the d orbitals hold 10 electrons. 10 electrons. 2 electrons can be held in these shapes. These shapes are essentially due to quantum mechanics. These shapes are basically regions where electron waves can exist. I'll leave it at that. But the way to think about it right now is here's a shape where electrons can coexist. And this is due to the Schrodinger equation that helps us visualize these energy levels. Okay, so let's just keep it at that. We're going to get into this detail. But if you just think, hey, these are the regions of space where electrons exist in the outermost shell for the transitional elements. Okay, that's what opens the door for the possibility. Also, they have multiple positives and they're pretty smaller. So having a large attraction for ligands, electrons, and having electrons in these regions create, okay, the scenario for colored solutions. Okay, so let me explain that. Okay, sapphires, okay, same idea. Okay, so how does this work? All right, well, the best way for me to do this is this, I think. Okay, so here is the +2 or the +7 if it's manganese. But let's think about copper. Okay, now I told you that there are 6 different shapes that 5 different orbitals that electrons can exist in. And these are the shapes. Okay, I also told you because of their size and how much charge they are, okay, water's oxygens get pulled in. That's called a ligand. Now it doesn't have to be oxygen, but I'm showing you that. So these little dots here represent the electrons from the ligand. In this case, water, because I'm dealing with the copper complex behind me. Okay, now we're going to learn that when we draw d orbitals, okay, we like to draw them in what we call orbital notation. And we'll draw 5 boxes. And the 5 boxes represent each different shape. And we use arrows. If I had 5 valence electrons, I would draw arrows to show that, hey, one of each would go in each box, each orbital. So one of these boxes is an orbital. That's a place where the electrons exist. All right? Again, it's really a wave function. Don't worry about it. Electron exists in that region. It still works the same way. Now, when the ligand approaches, remember, in the case of copper, the oxygen end of the water, negative, is really attracted to the copper +2. And only 6 can fit. So the water's going to repel each other to get a stable structure. That structure is called an octahedral. Octahedral. Okay? So the water's going to attack from the top and bottom. Okay? That makes sense? And then, this is hard to see, it's going to attack in a square. So here's a water attacking this way, a water attacking this way, and then there's a planar square in the middle where the water attacks this way. These are 90 degrees, by the way. And that's the octahedral. Okay, now, so if you can think about that, so this is actually a plane, but they're bringing it down so you can see it. 3 dimensions is important. Now, you notice the reason why we draw this orbital notation normally like this is to show you that this orbital has the same energy level. They have the same energy. This electron is the same energy as this electron. And this would be an energy diagram. Notice they do not have them drawn here this way. They're splitting them. And let me explain. If the negative oxygen is really attracted, has to be that way, and gets pulled in, and they're d orbitals, okay, and there's electrons in those orbitals, that's important too. Here's what happens, really important, okay? Now, sometimes those electrons from the oxygen will get pulled in right into that orbital that has electrons. Right in. And an electron that's forced to be close to an electron is going to do what? Repel each other, be high energy. That's why all of a sudden they split. And then sometimes electrons will go into this shape. These are two different orbitals. Let's just make them here and here. And what happens is if there's already an electron there and they get pulled in right where there's an orbital, those two electrons become high energy. They're repelling in there. And so what happens is these two are in a higher energy state. And now we just split the D's. Well, why don't these guys go up? Well, these guys are going in between the orbitals. In between the orbitals. I know you don't see with the boxes here, but these guys are not, they're being pulled in, but they're not going in where the electrons are for that particular shape, for that particular orbital. Here they're competing for the same space. So they're getting pulled in. Sometimes they get pulled in exactly where electrons could be, and sometimes they're getting pulled in where they're not. Two shapes of the d orbitals, they will always be pulled in exactly. And that's a place where you're going to have competing electrons, and that's where it's destabilized. Things that have high energy, destabilized. And there's our split, party people. There is what we call a little gap. We just made a little gap. What's so important about it? Well, party people, this is it. This is the crowning achievement of this theory. If I've got an electron here, and I shoot it a little bit of energy, like visible light. Visible light is not high energy. So the visible light is here. That electron can absorb that light and now jump here. We've created a gap for electrons to jump to. It's a small gap. Has to be because light is small energy. Are there naturally bigger gaps? Sure, but visible light is too low in energy to make electrons jump there, except if we shoot them with X-rays. Okay, we can actually rip the electrons away. So we're creating small little gaps, or water being pulled in, or some negative being pulled in places where there is places for electrons and overlap, create that high energy orbitals. We call it crystal field splitting of the D's. And that little gap allows electrons to jump. Now, party people, transitional metals make colored solutions. The last column doesn't. You're going to learn this, okay? But I want to show you why it doesn't, okay? So party people, back to our thing. Zinc, cadmium, mercury are not considered to be transitional because they fill their d orbital. This is a D1, D2, D3, D4. This is D10. If you put in all electrons here, if you fill them, they're still splitting, but electrons can't move because there's no room for them to move. So they don't make a color. Okay? So crystal field splitting is nothing more than the overlap of where these guys who get pulled in into regions where electrons are allowed to be, and it destabilizes or increases the energy level. Okay? Sometimes they get pulled in directly where electrons can be, and that makes it a higher energy, and some more enough, 3 of them, they get pulled in where the shapes aren't. If you just stay with that, we'll talk about that. And that's what creates a gap small enough to take in part of the wavelength. Okay? So here's how we normally draw the 5 boxes of D. We call them degenerate. They're the same energy level. But in a scenario where something gets pulled in as an ion, we'll split them. And that little change or gap is specific. If the gap is bigger, you need a higher energy light to jump. A blue is higher than an orange. Orange is higher than a red, right? And if you're absorbing a blue, you show what? You show what? Yellow. If you're absorbing a blue, okay, you show yellow. If you're absorbing yellow, yellow is a lower energy, you show blue, like copper does. So we can think of it that way. All right? Now, there's different colors depending upon what the ligand is. Some ligands affect that area better than others, okay? And that's why there's different colors. But you should be aware of some things that are natural. Our blood is red. Why is our blood red? Our blood is red because the iron plus 3 that's in our hemoglobin creates a ligand. Okay, now that ligand is 4 hemoglobin molecules. That's where the oxygen is held. There's 4 hemoglobin molecules that create a ligand. Now with water, it has that red color, but our blood is reddish or more maroon because of crystal field splitting. All right? And good times. So there is an example of hemoglobin. That's an Fe plus 3. Here are the 4 ligands that are doing what? Taking their electrons and doing what? Interfering with its d orbitals and creating a split. Enough so they can absorb wavelengths of light but not use red. That's why red blood cells are red. And these are the different beta chains. There's 4. This is a quaternary structure. Remember that? You take a what? A folded protein that's a tertiary structure. You put 4 of them there as heme groups. And as long as one of the ends attaches to iron, that's it right there. How about chlorophyll? Oh, Christmas. I just went back. Okay. Any case, you get the idea. All right. So, I didn't quite get a chance to talk. Oh, I have some time. So now I want to transition into spectrophotometry. That is the device that we're going to use that we did in AP Bio with chlorophyll to measure exactly the wavelengths of light. Okay? And this is important because your homework's based upon it, and it's also important because your next lab is based upon it. Okay? Okay, let's just do that. Now, by the way, there's a demo here where I have copper and water. There's the blue color. If I have pure chlorides is a different ligand, so it kind of affects the gap a little bit. Changing the ligand changes the color because it changes the gap. Okay? So, again, I know this is new to you and really very weird, but it should make sense. All right, so here's spectrophotometry. Okay, I'm sure there's a TikTok I can make, Bob, but I'm just going to teach you without a TikTok. Okay, now, spectroscopy is basically a way of looking at the individual wavelengths of light. We know that, hey, the red, Roy G. Biv right here. Red, orange, yellow, green, indigo, violet, blue. We got it. Any case, Biv, blue, indigo, violet. Okay, got it. Any case, the smidgen of the electromagnetic spectrum is visible light, and it's low energy, okay? And we've talked about this in other courses, but we'll talk more about this when we talk about the Bohr model of the atom when we get to those things. Bottom line is, okay, these guys have longer wavelengths, okay? Here's a long wavelength. Wavelength is this. Okay, so blue has a certain wavelength. Red, okay, blue has a wavelength and red has a longer wavelength. So if this was a red wavelength, it would have something like this. Not exactly drawn, but the longer the wavelength, okay, the lower the energy. Shorter the wavelength. Growing up, you guys didn't have this, but I remember as an adult, we had DVD players. They were red lasered. And all of a sudden they called them, oh, we got Blu-rays. Well, using a red monochromatic light to read the basically imprinting of the DVD only gave us a certain amount of data. By shooting a blue light that had a what? Smaller wavelength, would hit the surface more often and reflect back more information. So the Blu-ray gave us a heck of a lot more data. You could play high definition sound and video from Blu-rays. So interesting, during my lifetime, that was a big deal. But in any case, okay, let's get to what we're talking about. Every single type of light has a unique wavelength and definitely a different energy level. Okay, so moving forward, low energy over here, okay, greenhouse gases, vibration of, we vibrate molecules with that, microwaving food. And then high energy, hey, you break bonds, mutations in DNA, that's why you don't want to be around these guys. These guys are mutagens, okay? So something you should be aware of. And we know that we see at night because of infrared. It's not part of the visual spectrum. Infrared scopes basically measure thermal energy. Molecules move and give off. All right, remember there's 3 ways heat can move out of an object. Convection, convection, and radiation. Okay? So if you have an infrared remote and someone gets in the way of you, it can be blocked very easily. Okay? Any case, some basics that we did. Okay, spectrophotometry is about measuring what an object is using. We're going to learn an emission spectrum of hydrogen. If I take hydrogen gas and shoot electricity through it, it actually gives off only 4 different types of light with 4 different wavelengths. We later found out that light it gives off is based upon the energy levels of those electrons. We'll talk more about that. If we shoot white light at hydrogen, we get this, spots where there's missing light. That's the light it uses. And if you notice, it's exactly the light it's using to jump up. Okay? A jump from the 5th energy level to the 1st gives us a certain energy, a certain type of light. Okay? In fact, the 3 to the 2 is the lower energy red. Okay? And the 4 to a bigger jump gives us a more higher energy. Okay? This leap is that color. Now, if we shine white light, which is all the wavelengths, it uses that energy to jump, to go back from 3 to 2. We'll talk about that. So it's the gaps in electron energy levels that gives its ability to absorb energy, sometimes in the form of light. That's where we're headed. Okay? And this should be important to you because less than 20 miles away, we have the best white light source in the world. Okay? The Brookhaven National Lab. And they do all different types of data with it because if you can shoot a perfect white source, you're shooting out all the wavelengths. You can see what's missing, what chemicals are using to understand its structure or identify its compounds. Okay? All this stuff is around you and very close. Okay. So yeah, so that is showing us where. That's the energy it takes. So if I shoot white light, that wavelength that's in that perfect white light spectrum, it's going to use that little smidgen of it to jump up. Okay, that's what we're talking about in absorbing. So it's missing. It's missing. Spectrophotometers measure what's missing. Okay, we shoot a white light. Okay, and see what's missing. That's important. Okay, all right, moving through. So what is a spectrophotometry? It's a device. We put a sample in a cuvette. Okay, now it's got to be a colored sample. If it's a clear sample, I'm not going to measure anything missing. What a spectrophotometer does is shoots a light source with all of the spectrum, with all of the wavelengths of light. And it goes through the sample, and the detector measures what gets through. Okay? What gets through is called transmittance, and it's a ratio. Here is the what's getting through over the total. Hey, that's going to be a fraction. This is a lot, and this is going to be something missing. This number is going to be less than 1. Absorbance is what we're actually going to measure. It's negative log of the transmittance. I'll explain in a second. Okay? It makes perfectly good sense. So, spectrophotometer, here's a cuvette. We're going to take a colored sample, like copper solution. We're going to shoot a light through it. Okay? White light. Okay? Not all that white light is going to come back out because it's going to absorb certain energy levels of the visible light. So something's going to be missing. What's missing, notice it's lighter, is the transmittance. And transmittance is this amount less over the big. So it becomes a what? It becomes a number less than 1. Okay? Now, in our reference tables, we have A equals ABC, a hard one. Okay? And what this is absorbance equals a constant times the distance in the cuvette times the concentration. And there is the link. We can solve for the concentration of that colored solution based upon what's missing in the spectrophotometer. That's the key. We can solve for the molarity, okay, based upon what's missing. And it makes sense. If I have a more concentrated solution, yes, isn't there going to be more missing light? There's more chemicals that have a gap that can absorb more light. So if there's more chemicals with this little gap because of crystal field splitting, it's going to take more of that wavelength and more is going to miss. If it's a, what? Lower concentration, which means what? The color won't be as dark. There'll be what? More of this because there's less chemicals to absorb that light. Okay? So that's what that comes from. Okay, still stay with me, we're not done. So here's what we get. This is a more concentrated solution of copper ions. It's less concentrated. Here comes the white incident light. The transmitted light is what's not being used. Okay? So we're missing some. Why are we missing some? Because the chemical is absorbing some of that light based upon its electron structure and how many of them. This is a darker solution, so there is more of the copper. Therefore, there's more absorption of the light. So you can see that in a higher concentrated compound, a darker solution, the amount of light that gets through is lowered. The transmitted light that gets is lowered. Why is it lowered? Because there's more of the copper to absorb that light. And so the transmittance drops. So the more concentrated that colored solution is, the less light that gets through. That makes sense? Right, if you have less of the chemicals there, there's less absorption going on and more light gets through. That's how that works. That's why we can solve for the concentration. But nobody likes higher concentration means lower light. No one likes the numbers getting smaller. So what they do is, instead of transmittance, they convert it to absorbance. This is showing us what? How much light is going through, which is going to be lowered in a what? Higher concentration. We want to convert that to absorbance. How much is the solution absorbing? Isn't this absorbing more light? But we're getting a lower number. We don't like that. So we're going to take the light that gets through, and we're going to do a negative log. What does that do? First of all, it makes a number that's less than 1 become greater than 1. And it makes it go up. So that's what we do here. All right? So here is our values. And because absorbance is a negative log of 0.8, it becomes, instead of, it becomes 0.1 or 0.10. It doesn't seem like a big change here. But as there's what? Less light getting through transmitted, we make that what? Oh, a bigger number by negative logging it. So absorbance, all it does is negative log of the transmittance to make it a bigger number. So clearly, as this gets more concentrated, the absorbance goes up. The ability of the chemical to absorb more, which means less transmittance, goes up. And that's how that works. Okay? So we use absorbance, which is a measure of how much the chemical. And we do it because we want to convert an inverse relationship. Hey, greater the concentration, lower the transmittance. Lower the amount of light that comes out. We don't care about that. This guy is absorbing more light. That's why there is less going out. So therefore, we do negative log of the transmittance to come up with the absorbance. And that's what we're doing in a spectrophotometer. Okay? Where are we? Okay, and so what we're going to do, oh, Christmas, where am I? Last little piece. If I go back to, I think I have this picture here. No, I don't. Get out of here for a second. Back up here. Okay, this is absorbance. This is absorbance. And so the chlorophyll was great at absorbing, these are wavelengths, absorbing these wavelengths. So here's what we're going to do. Okay, we're going to take a spectrophotometer and we're going to put in the copper solution. Now, what is the lab? Well, we're going to find the percent by mass of copper in brass. What is brass? Brass is an alloy, a substitutional alloy of copper and zinc. Stay with me. So we're going to take brass. This is our lab that you're going to do when you come back. And your homework is based upon this. We're going to take brass, which is basically copper, some zinc, and a copper crystalline compound. And it's a substitutional alloy because they're about the same size. I'm going to take a known amount of brass, and we're going to find the percent by mass of copper in it. We're going to take this sample of brass. We're going to add nitric acid. Why am I adding nitric acid? Because the nitrate ion will react all of this into NO2, but it's going to make a solution of zinc plus 2 and copper plus 2. Does the zinc have a color? No, it has a complete set of electrons in its boxes. Nowhere to move. Copper is going to give you a blue color. We're going to put that blue color into a cuvette. Cuvette is a little rectangle that goes into the spectrophotometer. And then we're going to get an absorbance. Now the first thing that we do is this. We get this kind of thing that goes up, that looks like this. And this is going to give us a wavelength. And this is going to give us an A. And this tells us, hey, there is one particular what? Wavelength that copper loves to absorb on white light, correct? It can absorb a whole bunch of, just like chlorophyll. We're going to take that wavelength, it might be 600 or something, I don't know exactly, and we're going to take the spectrophotometer and we're going to tune the spectrophotometer to that exact wavelength. We're going to just look at that. So the first step was you put the sample in, we'll get this big range of wavelengths it can accept because of the what? Crystal field splitting. And then we're going to tell the spectrophotometer, just look for the one you're the best at looking at, so the peak height. Then, here's what we do. Now that we've tuned it, we set the absorbance up, and now we just start measuring. And we can measure that A. And then we go from there. All right? I know that you don't got it all. So tonight's homework, I gave you a copy. I have a video I'm going to make. You're going to look at this weekend's homework. I'm going to go over all the parts of that lab, and then I'm going to give you a form that helps you practice that. Have a believable weekend.
Do you want the lab that we did?
If you have the lab, I'll take it.